Now, let's talk about the chemistry that's going on. So far, we've talked about the process of the titration. I'm going to get NaOH and HCl. I'm going to standardize each one of them. I'm going to take a sample of antacid. I'm going to add it to my flask, crush it up, make sure it dissolves, and titrate the antacid through the process of a back titration. So I add extra acid to the flask, neutralize out everything, and then I titrate it with NaOH. But I need to talk about the chemistry before we go any further. Alright, so I take an antacid. The antacid in your case is going to be calcium carbonate. We're going to supply you with a Tums tablet. And that Tums is calcium carbonate. There's a number of milligrams on that tablet. We know what's supposed to be there. So calcium carbonate's going to be there. It's your job to figure out how much. With the calcium carbonate, we are going to add hydrochloric acid to it. And a reaction is going to happen. And a double replacement reaction, just like NaOH and HCl, will go forward. So I've got this calcium, and I have this hydrogen, and they're going to switch places. So instead of CaCO3, I'm going to end up with a Ca and a Cl that come together in a beautiful marriage. However, the calcium is a positive 2 charge, and the chlorine is a -1 charge. So that means I need another chlorine to make that molecule balance. You have to take it one step at a time. This comes from the anion-cation charts. So it's really CaCl2. That's what needs to go there. All right. And then I'm going to add to that, instead of an HCl, it's going to be H and a CO3 group. So an H and a CO3. All right, well, hydrogen is a +1. A carbonate is a -2. So this is not going to work for me either. I need to make that balance and make it work. So I'm going to have to put a 2 there. So that way I get a +2 and a -2, and they cancel each other out. Now I've just balanced that molecule. So these are the products that will happen when I take the antacid and react it with a acid. I get calcium carbonate, which is a salt, or calcium chloride, which is a salt really, and I get H2CO3, which is carbonic acid. Well, the story with carbonic acid is that it doesn't stay around long at all. Carbonic acid breaks down, and it breaks down into a CO2. So take out the carbon, take out 2 of the oxygens, and what I'm left with are 2 hydrogens and 1 oxygen. So this breaks down to CO2 and water. So for some of you, when you eat an antacid, a Tums or a Rolaids, or you drink that milk of magnesia, sometimes you feel a little gassy, right? Don't want to talk about it that much, but maybe you feel a little gassy, a little bloated after you do that. And the reason is because this reaction's producing carbonic acid, which breaks down automatically to CO2, which is carbon dioxide gas that you begin to burp up or flatulate out. Okay, so that's where all of that gas is coming from. Now, the key here is that in a laboratory setting, we want to make sure that this H2CO3 goes to completion. We want to help that CO2 production when we can. So that is the process of heating. That's why we heat these samples up. We heat them because we want to drive off this H2CO3. We want that to break down to CO2 and escape and leave out of my beaker, or my flask that I'm getting ready to titrate in. So that is the whole concept of heating your sample while you do it. You want to drive off that gas because you do not want to cause that an embarrassment with your lab grades. All right? Much less your neighbors. Okay, so I need to make sure that I know how to balance this equation, right? I mean, we have to have a balanced chemical equation before we can do anything. So I just want to make sure that this is okay. I've got one calcium. I've got one CO3 group, and here I've got one CO3 group. I know this breaks down, but it's a one-to-one relationship, right? A carbon and two oxygens come down, and the two hydrogens and the oxygen marry up to make water. So that's why I don't really include this in the balancing. It's already kind of taken care of if I go back to the original. I've got one hydrogen here, but I've got two hydrogen there. So I need to put a big 2 out in front. And then this gives me 2 chlorine by doing that. And over here on this side, I've got 2 chlorine from my calcium chloride. So by balancing the chemical equation, the only thing that I have to do is put a big 2 out in front of the acid, and I'm set. All right, so this is the equation that is happening at the molecular level when you begin to titrate this reaction. All right, so let's talk about calculations. Now that we've got this background on the equation, let's talk about the calculations. And we're first going to start with the standardization of NaOH. Or I mean, not NaOH, but HCl. Okay. In my burette, I've got sodium hydroxide. And I know the concentration. In my flask, I've got hydrochloric acid. And I know how much because I pipetted. It's up to me to figure out the concentration of that acid. All right, so over to the side. Hydrochloric and sodium hydroxide will react together to give me water and sodium chloride, salt. It's a 1 to 1 to 1 to 1. Everything's balanced. The titration will stop when I see the color change that goes from yellow to blue. And then I get the number of milliliters of NaOH that it took from up here at the top. All right, so let's say that the concentration of my hydroxide is 0.1043 molarity. And let's say that the titration took 5.73 milliliters of NaOH. That's when I got my color change. Well, I need to figure out the concentration of my hydrochloric acid. But I know from the very beginning, maybe I was told to pipette 15 milliliters of hydrochloric acid into that flask. But I know at least the volume. It'll be there for me. It will tell me how much I needed to use. So I need to come up with a way to figure out what the concentration of the acid is. So let's work through the steps. All right. If I know the molarity of sodium hydroxide, and I know the liters of sodium hydroxide that it took to titrate. Now this is mils, so I'm going to convert it over to liter, because that's my molarity formula, right? Molarity is equal to moles divided by liter. I know the molarity of the NaOH. I know the volume of NaOH that it took. So I can use my handy-dandy calculator in order to solve how many moles of sodium hydroxide it took to titrate this sample with. 0.00573 times 0.1043 equals. So I get 0.0005976. All right, so moles, 0.000, and look, I already forgot it, 5976 of NaOH. All right, so I'm going to circle that number, and that comes straight from the molarity problem. So it took this many moles of sodium hydroxide to neutralize my hydrochloric acid that was in this flask down below. Well, this is a 1 to 1 to 1 to 1. So that means if it took this many moles of sodium hydroxide, it's also going to take that many moles of hydrochloric acid, because it's the same ratio, 1 to 1 to 1 to 1. Okay, well, if I know the moles of hydrochloric, and I know how many milliliters of hydrochloric that I started with from the very beginning, because I pipetted that number, I can come up here and you can use another molarity problem, because that's what we're after, this concentration in molarity. The moles of HCl, 0.0005976, divided by the liters of hydrochloric acid that I started with. So that's 15.015 liter is 15 mils. So I can take those two numbers, divide them, and I get a concentration of 0.0398. So based on these numbers that I've provided, just made them up, the concentration of my hydrochloric acid is going to be 0.0398 molarity. And this is the first half to solving how much antacid is in that tablet. So again, I know the concentration of NaOH. It's been standardized already for me. I just have to assume that that number is true. I know how much volume it took to titrate. I take those two numbers and plug it into the molarity problem down here. I know my molarity. I know how many mils it took. I solve for mole. This tells me amount. This is how much NaOH, molecule-wise, it took to neutralize out the acid. Well, it's a 1 to 1 to 1 to 1. So if that's how many moles of NaOH it took, that's how many moles of HCl that was in that flask. They're equal. If I know the moles of hydrochloric, and I know the liters of hydrochloric that I started with in my flask that I pipetted, I can take those two numbers now, plug those into a molarity formula, divide them, because that's mole divided by liter, and that will give me molarity of my HCl solution. And this is for the standardization step. So this is just first half of the calculations. We still have the calculations to do for the antacid, but this is the first half of the standardization step. So in the next video, we'll talk about the calculations that you need to do when it concerns the antacid. And we're going to go back up here and focus on this equation once again.